When dealing with multiple service entrances in a building, particularly in a warehousing context with sensitive refrigeration equipment, the question of how to properly bond those services together becomes paramount. The goal of bonding is to create a low impedance path for fault current to return to the source, ensuring that overcurrent protection devices operate quickly, clearing the fault and minimizing the risk of electrical shock or fire. There are several key factors to consider when deciding between relying on the building's steel structure for bonding and installing a dedicated copper bonding conductor, such as a 4/0 copper conductor. Let's delve into the adequacy of using the steel structure for bonding electrical services. Firstly, a steel structure must provide continuous electrical continuity between all service entrance locations. This means that there should be an unbroken, low-resistance path throughout the entire steel framework. Any breaks or high-resistance connections can compromise the effectiveness of the bonding system. Secondly, the steel members must have a sufficient cross-sectional area to safely carry the maximum available fault current. If the steel is undersized, it could overheat during a fault condition, potentially leading to a fire or structural damage. The fault current carrying capacity of steel is significantly lower than copper for a similar cross-sectional area. Thirdly, all connections between steel members and between the steel and the service equipment must be secure and exhibit low electrical resistance. Connections that are loose, corroded, or painted can significantly increase resistance, hindering the flow of fault current. Proper bonding techniques, such as using listed bonding jumpers and appropriately tightening hardware, are essential. While utilizing the building's steel might seem like a cost-effective option, a dedicated copper bonding conductor offers several distinct advantages. Firstly, guaranteed continuity. Copper is an excellent conductor of electricity, providing a reliable and consistent low-impedance path for fault current. Unlike steel, copper is less susceptible to corrosion and provides a more predictable electrical path, even in harsh environments. Secondly, high current capacity. Copper conductors are capable of carrying very high fault currents without overheating. A 4/0 copper conductor, for example, has a substantial ampacity rating, providing a significant safety margin in the event of a ground fault. This high current carrying capacity ensures that the overcurrent protection devices will operate quickly and effectively. Thirdly, enhanced grounding. A dedicated copper bonding conductor can also serve as a grounding electrode conductor connecting to a grounding electrode system. This enhances the overall grounding system of the building, providing a low impedance path to earth for dissipating fault current. The grounding electrode system typically consists of ground rods, ground rings, or connections to the building's metal water pipe. Now let's discuss the recommended approach. While the steel structure might offer some level of bonding, relying solely on it is generally not recommended. A dedicated copper bonding conductor provides a more reliable, safe, and code-compliant solution. Firstly, reliability. A copper bonding conductor provides a consistent and predictable bonding path, regardless of the condition of the steel structure. This is particularly important in older buildings where the steel may have corroded or connections may have deteriorated over time. Secondly, safety. A dedicated bonding conductor significantly reduces the risk of electrical fires or shocks in the event of a fault. By providing a low impedance path for fault current, it ensures that overcurrent protection devices operate quickly, clearing the fault and minimizing the potential for dangerous voltage on exposed metal parts. Thirdly, code compliance. Most electrical codes, such as the National Electrical Code, or NEC, require a dedicated bonding conductor for connecting service entrances together. The NEC provides specific requirements for the size and installation of bonding conductors, ensuring that they are adequate for the anticipated fault current levels. In summary, while the steel structure may contribute to the overall bonding of the electrical system, it should not be relied upon as the sole means of bonding multiple service entrances. A dedicated copper bonding conductor, such as a 4/0 copper conductor, provides a more reliable, safe, and code-compliant solution. For optimal safety and performance, it is recommended to install a copper bonding conductor to connect the grounding electrodes of the three services. Let's consider some specific NEC requirements related to bonding and grounding. NEC Section 250.24. C addresses the grounding electrode conductor for a separately derived system which is applicable to multiple service entrances. This section requires that the grounding electrode conductor be sized according to NEC Table 250.66, based on the size of the ungrounded conductors. For example, if the ungrounded conductors are 500 kcmil copper or 700 kcmil aluminum, the grounding electrode conductor must be at least 1/0 copper or 3/0 aluminum. NEC Section 250.28 covers bonding jumpers and specifies requirements for their size and installation. The bonding jumper between service enclosures must be sized according to NEC Table 250.102. C1, based on the size of the service entrance conductors. For instance, if the service entrance conductors are 500 kcmil copper, the bonding jumper must be at least 1/0 copper. NEC Section 250.64. E addresses the installation of grounding electrode conductors and bonding jumpers. This section requires that the grounding electrode conductor and bonding jumpers be installed in a manner that protects them from physical damage. They must also be securely fastened to the surface on which they are carried. NEC Section 250.104 covers the bonding of metal water piping systems. This section requires that the metal water piping system be bonded to the service equipment enclosure, the grounded conductor at the service, the grounding electrode conductor, or the grounding electrode system. The bonding jumper must be sized according to NEC Table 250.102. C1. NEC Section 250.104. B covers the bonding of other metal piping systems and metal frameworks. This section requires that metal gas piping systems and other metal piping systems that may become energized be bonded to the service equipment enclosure, the grounded conductor at the service, the grounding electrode conductor, or the grounding electrode system. The bonding jumper must be sized according to NEC Table 250.102. C1. NEC Section 250.118 lists acceptable grounding conductors and bonding jumpers. This section specifies that grounding conductors and bonding jumpers must be made of copper, aluminum, or copper-clad aluminum. They must also be sized and installed in accordance with the NEC requirements. NEC Section 300.3. B requires that all conductors of the same circuit, including the grounding conductor, be installed together in the same raceway or cable. This ensures that the impedance of the grounding path is minimized, allowing for the quick operation of overcurrent protection devices. NEC Section 314.4 covers the use of metal boxes and enclosures. This section requires that metal boxes and enclosures be bonded to the grounding system. This can be achieved by using listed grounding bushings or by bonding the metal box to a grounding conductor. It's crucial to remember that electrical codes are constantly evolving, so you should always consult the latest edition of the NEC and any applicable local amendments to ensure compliance. Licensed electrical contractors are trained to understand and apply these codes correctly. When performing electrical work, safety should always be the top priority. Always de-energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as insulated gloves and safety glasses. If you are not comfortable performing electrical work yourself, it is best to hire a qualified electrician. They have the knowledge, skills, and experience to perform the work safely and in accordance with all applicable codes. Proper grounding and bonding are essential for the safety of people and property. A properly grounded and bonded electrical system will help to prevent electrical shocks, fires, and equipment damage. By following the NEC requirements and best practices, you can ensure that your electrical system is safe and reliable. Let's talk about some best practices when installing a copper bonding conductor. Firstly, select the appropriate size conductor. The size of the bonding conductor should be based on the size of the service entrance conductors and the available fault current. Refer to NEC Table 250.66 and 250.102. C1 for guidance on selecting the correct size conductor. Secondly, use listed connectors. Use only listed connectors that are specifically designed for grounding and bonding applications. These connectors will ensure a secure and reliable connection. Thirdly, make clean connections. Ensure that all connections are clean and free of corrosion. Use a wire brush or emery cloth to clean the conductors and the surfaces of the connectors before making the connection. Fourthly, tighten connections properly. Tighten all connections to the manufacturer's specified torque. Over-tightening or under-tightening can compromise the integrity of the connection. Fifthly, protect the conductor from damage. Protect the bonding conductor from physical damage by installing it in a conduit or raceway, or by using a cable with a protective jacket. Sixthly, label the conductor. Label the bonding conductor clearly so that it can be easily identified. This will help to prevent accidental disconnection or damage during future maintenance or modifications. Seventhly, inspect the installation. Inspect the installation carefully to ensure that all connections are secure and that the conductor is properly protected. Eighthly, document the installation. Document the installation, including the size and type of conductor, the location of the connections, and the date of the installation. This documentation will be helpful for future maintenance and troubleshooting. Here are some common mistakes to avoid when installing a copper bonding conductor. Firstly, using undersized conductors. Using an undersized conductor can compromise the effectiveness of the bonding system and increase the risk of overheating during a fault condition. Secondly, using improper connectors. Using improper connectors can result in a loose or unreliable connection, which can increase resistance and reduce the effectiveness of the bonding system. Thirdly, making corroded connections. Corroded connections can significantly increase resistance and hinder the flow of fault current. Fourthly, over-tightening or under-tightening connections. Over-tightening or under-tightening connections can damage the conductors or connectors and compromise the integrity of the connection. Fifthly, failing to protect the conductor from damage. Failing to protect the conductor from damage can result in a broken or damaged conductor, which can compromise the effectiveness of the bonding system. Sixthly, failing to label the conductor. Failing to label the conductor can make it difficult to identify the conductor in the future and can increase the risk of accidental disconnection or damage. Seventhly, neglecting to inspect the installation. Neglecting to inspect the installation can result in undetected problems that can compromise the effectiveness of the bonding system. It is important to also talk about maintenance and testing. Routine maintenance and testing are essential to ensure that the bonding system continues to function properly over time. Firstly, visual inspection. Perform a visual inspection of the bonding conductor and connections on a regular basis to check for signs of corrosion, damage, or loose connections. Secondly, continuity testing. Perform a continuity test to verify that there is a continuous low impedance path between all bonded parts. Use a multimeter or a specialized grounding and bonding tester to perform this test. Thirdly, resistance testing. Perform a resistance test to measure the resistance of the bonding path. A high resistance reading indicates a problem with the bonding system. Fourthly, torque testing. Periodically check the torque of all connections to ensure that they are properly tightened. Use a torque wrench to tighten the connections to the manufacturer's specified torque. Fifthly, infrared scanning. Use an infrared scanner to identify hot spots in the bonding system. Hot spots indicate areas of high resistance, which can be a sign of a loose or corroded connection. Sixthly, record keeping. Keep records of all maintenance and testing activities, including the date of the activity, the results of the tests, and any corrective actions taken. These records will be helpful for tracking the performance of the bonding system over time. In conclusion, the proper bonding of multiple service entrances is essential for the safety of people and property. While the building's steel structure may provide some level of bonding, a dedicated copper bonding conductor provides a more reliable, safe, and code-compliant solution. By following the NEC requirements, best practices, and routine maintenance and testing procedures, you can ensure that your electrical system is properly grounded and bonded. Always prioritize safety when working with electrical systems, and consult with a qualified electrician if you have any questions or concerns. Remember that electrical codes and standards are subject to change, so it is important to stay up to date on the latest requirements. By investing in proper grounding and bonding, you can protect your building and its occupants from the hazards of electricity. The choice between using the building's steel structure and a dedicated copper conductor for bonding multiple service entrances hinges on prioritizing safety, reliability, and code compliance. While the steel structure might seem like a convenient and cost-effective option, it often falls short in providing the consistent and dependable grounding path necessary to ensure adequate protection against electrical faults. A dedicated copper conductor, on the other hand, offers several advantages. Its high conductivity ensures a low impedance path for fault currents, allowing protective devices to quickly trip and clear the fault. Copper is also less susceptible to corrosion than steel, ensuring long-term reliability of the grounding system. Moreover, a dedicated copper conductor provides a more predictable grounding path, making it easier to test and verify the effectiveness of the grounding system. Building codes typically favor the use of dedicated copper conductors for grounding and bonding purposes. These codes are designed to ensure the safety of people and property, and they reflect the best practices in electrical engineering. Relying solely on the building's steel structure for grounding may not meet these code requirements, which can lead to potential liability issues. Ultimately, the decision of whether to use the building's steel structure or a dedicated copper conductor for bonding multiple service entrances should be based on a careful assessment of the specific circumstances, taking into account safety considerations, code requirements, and long-term reliability. In most cases, the added cost of a dedicated copper conductor is a worthwhile investment that can provide peace of mind and protect against the potentially devastating consequences of electrical faults. When working with electrical systems, it is always best to err on the side of caution and prioritize safety above all else.